Hello everyone. As you can see, I now have a whiteboard. I was hoping it would be a little bigger. It looked bigger on the picture on Amazon, but I think it's probably better than nothing, probably better than you just watching the back of my hand for an hour. So hopefully this is an improvement. And when you get to the end of this, if you thought there were any problems with it, either technical or explanation wise, please let me know and we can try and address those. Okay, so today is lecture number 16. We are now on chapter 11, so we're going to be starting nuclear physics today and learn about the dynamics of the nucleus and different kinds of radioactive decay. So change pace. We're going to cover stuff that's on pages 493 to 521. For next class, please read 522 to 541. Homework, I will assign soon, maybe even in the email that I write to you when this is done uploading, which probably won't be till tomorrow, unfortunately. So, today we're going to talk about the nucleus, nuclear stability, and we're going to start talking about nuclear decay. Okay. So, the first discovery of radioactivity was in 1896 by A.H. Becquerel. I have no idea if I'm saying that correctly or not. Becquerel was investigating the fluorescence of minerals after exposed to sunlight, and what he did serendipitously by accident was he put one of his photographic plates beneath one of the fluorescent materials that he was studying, but then he did this in a locked, maybe not locked, but a closed drawer away from any kind of light source, so impossible for there to be some fluorescence. Fluorescence is the absorption and re-emission of electromagnetic radiation. So he did this where this object couldn't fluoresce, and he still saw that on the photographic plate there was some image of the thing that he was investigating. So between 1900 and 1903, Ernst Rutherford continued to study this new thing that was termed radiation. Radiate at the time meant for things to, well, still means for things to move through space in every direction, right, as this new influence appeared to do. And of course they didn't really know when they were starting to study this what was going on, but what he discovered was he could classify radiation into three different types. Called them alpha rays, beta rays, and gamma rays. Pretty direct, they're just the first three letters of the Greek alphabet. But they go in an order, right? In decreasing order of penetration, and increasing order of ionization. You know what? I just remembered I have some tea, Stephen. Pause. In the back with my tea. Okay. So, the reasons that these two things are inverse should be apparent pretty quickly. If something is able to penetrate deeper into something, well, that means it's not running into things that stop the radiation, right? If I have some bulk material, say, right, some block of, I'm not drawing this very well, but you're familiar with that by now. If I have some block of material and mysterious green radiation is coming in, well, if it's hitting the surface and ionizing things in the surface, interacting with stuff in the surface, that's absorbing this radiation, so it doesn't penetrate very far into the material. Likewise, if it's not ionizing enough, well, then it can penetrate deeper into the material because the ionization reaction is what absorbs that radiation. So these two things being inverse should be pretty apparent. Okay. So black marker go? What? So the reasons for this stayed a mystery for a little while, until 1928, when George Gamow correctly predicted the rates of alpha decay by modeling it as a particle quantum tunneling through the nucleus, right? So this is sort of a barrier penetration problem now, right? So we learned about barrier penetration when we talked about the quantum well, that if we have a finite quantum well, right, say with some barrier, even though the thing we may be talking about is only in here, we get from various continuity conditions the fact that there is some probability for that particle in a box or whatever it is to tunnel through this potential barrier and end up on the either side. So by correctly predicting the rates of alpha decay as a nuclear tunneling problem and a nuclear barrier penetration problem, he showed that this radiation was a nuclear effect, a quantum nuclear effect. So since we're studying nuclear radiation decay, we'll start with some definitions for the nucleus. Now that I'm looking at this thing, I realize that it's cutting off the top of my head. Let me pause it and readjust. Okay, so that's hopefully a little better. So just to remind you, the nucleus looks something like this. So this is deep inside the atom right at the very center, and inside the nucleus we have quarks. These quarks are all flying around. Excuse me, we have nucleons composed of quarks. Nucleus, we have protons, neutrons, each of which is itself composed of 3 quarks. So a little while back we learned about the nucleus, we learned about quarks. We saw that each nucleon, either a proton or a neutron, is composed of 3 quarks, and we have the strong nuclear force that both binds the quarks themselves into the nucleons and we have a residual force, right, that binds the nucleons together themselves via this strong interaction between these quarks. So this is not the strong nuclear force, the thing that binds together the nucleus, which I'm pretty sure I've talked about before, isn't itself really a fundamental force. The strong nuclear force at the fundamental level is binding these quarks together. And as we'll see as we go through this topic, it's not this same strong nuclear force that directly binds together the nucleons into the nucleus. It's more rather a constituent force built up by the interchange of quarks and particles, not really quarks, but particles between the nucleons that themselves are carriers of the strong nuclear force. So the strong nuclear force directly binds the quarks into the nucleons, and some kind of force that's built on top of that strong nuclear force, almost but not quite, sort of a multipolar force, is what binds the individual nucleons together into the nucleus. So if we're to put a length scale on here, this is about 1 to 10 femtometers, where 1 femtometer is 10 to the negative 15 meters. So teeny, 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 tiny. Okay. So now continuing, what do we need to erase? Yeah. So continuing on with some definitions. A, atomic mass number. Okay. That's the total number of nucleons in the nucleus. And then we have N, which is the neutron number. Obviously, number of neutrons in the nucleus. And we've got the atomic number, Z, which is the number of protons. Right? So that should all be, so this is protons, this is nucleons, and I don't need to write subscript for neutron number because that should be obvious, it's the number of neutrons. Okay. So we have A equals n plus z. There's no other things in there besides neutrons and protons and the things that fly around between them and bind them together. Okay. And this z is usually roughly half A. Why isn't it exactly half? Well, we'll talk more about that. And if we are writing the name of an element, right? So O N A Z. Okay. So this is here where this O is, right? That's the atomic species. Any kind of chemical symbol can be put in there. So for an example, we'll do oxygen, right? Which is 1587. Okay. So we have 7 neutrons, typically, right? We have 8 protons, and we add them together for 15. Right? Typically, you don't see it written with all this other hoobajoo. You just see it written like that, which is probably what you're familiar with, right? So if two elements have the same Z, but are otherwise different, they're an isotope. Okay. If they have the same N, but are otherwise different, they are called an isotone. If they have the same A, they are called an isobar. Right, so elements of the same species can have differences in these numbers, and that's what makes them isotopes, right? So we want to build at least kinda accurate quantum model of the nucleus, but there are a few difficulties. One is there are 2 types of nucleons, which is a complication. Any complication obviously makes things more difficult. There are several types of emission or absorption. Not just photons. Right, when we're talking about regular atomic transitions, where we have 2 atomic levels, an electron goes up, it goes down, it either absorbs or emits a photon. Right, this was simple because the only thing happening was either that electron was absorbing a photon and moving up an energy level, where it was dropping down and emitting a photon. But now we're going to have not just one type of radioactive decay, but several. There's at least those 3, alpha, beta, and gamma, and things are even more complicated than that. And number 3, though we have a very good understanding of the electrostatic potential, that's what we have when we have those electron transmissions between its different energy states, the nuclear potential, or rather the nuclear potential function, is not entirely understood. Okay. And the reason for that is those complications I was talking about earlier when I showed, or not showed, but told you, I didn't demonstrate with nucleons, when I told you that it's a more complicated sort of residual force that binds together the nucleons, right? So we'll start with the properties of the ground states of the simplest case, right? So we're going to talk about the nucleus, but the nucleus as it's sitting there not doing anything, because before we want to talk about how it transitions between different states, we want to talk about what it's like when it's just sitting there, obviously, right? That's where we should start. So via scattering experiments that we know that the atomic radii are about equal to the atomic number to 1/3. Excuse me, the atomic mass number equal to 1/3. I'm going to make that mistake a lot, I'm sure. A is the atomic mass number. Z is the atomic number. I can't keep it straight, so good luck. I'll try my best. Okay. We can write that as radius is equal to some r naught, right? Some normalization times a to the 1/3. Okay. And this r naught, you might think of the basic units of the size of a nucleus. This is 1.2, give or take, 0.2 femtometers. Okay? Now that means that the volume of the nucleus, because volume is distance squared, the volume of nucleus is about A, which is fairly convenient. Okay. So the densities of all nuclei are about the same, right? These I erased it. Those nucleons are distributed more or less evenly throughout the nucleus, right? There's no weird substructure. Well, there's lots of weird substructure, in fact, but none of it impacts the density very much. Okay. So we know that the volume of this nucleus is about the atomic mass number. Okay. Nucleons are distributed fairly evenly throughout the material. There's another thing, material of the nucleus. There's another thing where density is fairly constant, and that's with a liquid. Right? So that gives us the liquid drop model of the nucleus. People will get a long ways just by modeling the nucleus of an atom as a drop of nuclear liquid, essentially. So that may sound very strange for there to be a liquid or material that's just a nucleus, but outside the nucleus, such things even exist in nature, right? If you're familiar with your astronomy, you may have heard of something called a neutron star. And what a neutron star is this a star that's not quite massive enough to make it up to being a black hole. Okay, so to give you the 1 minute explanation, and I'll expand on this later after we're done with this nuclear stuff. The 1 minute explanation of what's going on with stars is they start off with some amount of fuel. You know, stars in the early universe population, I forget, I think the numbering goes in reverse. The original population of stars was almost all hydrogen. Right? The universe pretty much only made hydrogen to start with very small amounts of helium and almost nothing of anything else. So stars that have a lot of hydrogen, right, they get hotter and bigger as they go through their lives. On the one end of the spectrum, there's things called brown dwarfs, which are stars that never really got quite big enough for much nuclear fusion to go on. Basically, really big gas giants made of hydrogen. Okay. As you go up in the mass of how much hydrogen you have compactified into a star, you go through different types of stars that have different life cycles. You get up to the most massive stars. When those stars die, they collapse down into a black hole, which is a rip in space-time. and all the strange, interesting stuff that goes on with them, which unfortunately is not part of this class. Other than that one lecture Lino did about general relativity, in which maybe he mentioned it. Okay. What if you're just below that threshold, right? What if you don't have quite enough mass to become a black hole at the end of your life, but you've still got a lot of mass? Well, what can happen is you can turn into a neutron star. Dream big. A neutron star is a star that's so massive that it's collapsed down to the point that there's only one thing holding it together, right? Keeping it from collapsing more into becoming a black hole, and that thing is actually the Pauli exclusion principle. Right? Neutron stars are so called because they're composed almost entirely of neutrons. Right? And the reason that the mass of those incredibly heavy material that's made only of neutrons doesn't collapse further is that the Pauli exclusion principle keeps them from becoming or moving into the same space, right? If they were bosons, they would be able to do that, and if they would just, I don't know what would happen, collapse more, essentially. But the Pauli exclusion principle on a star composed almost entirely of neutrons keeps those neutrons from collapsing further. So imagine this is a star that's made up of only neutrons, is essentially a giant atomic nucleus. If you took a tablespoon of this material, a tablespoon full of neutron star goop, it would weigh as much as a mountain, essentially. Right? There's that much mass packed into each little bit because it's just pure neutrons, essentially. So the book is a little bit of an example problem. This is example 11-3. Radius of a neutron star. In certain supernova events, the envelope of a star is blown away, leaving a core consisting entirely of neutrons. This stellar remnant is called a neutron star. And its density is approximately the same as that of an atomic nuclei. Compute the radius of a neutron star, whose mass is equal to that of the Sun. So the mass of the Sun is the astronomical symbol for Sun, in case you haven't seen it. Mass of the Sun is 1.99 times 10 to the 30 kilograms. Right, so essentially 2 with 30 zeros after it, kilograms. Excuse me. The mass of a neutron star, of course, is just density times volume. And that density is 10 to the 17 kilograms per meter cubed. All right, so if you had a meter cubed of neutron star, it would weigh, or rather, it would mass at 10 to the 17 kilograms. Right? So that tablespoon is the mass of a mountain. Okay. So, you get mass of the Sun, 1.99 times 10 to the 30th equals rho v equals 10 to the 17. 10 to the 17 kilograms per meter cubed times 4 pi r cubed over 3. So we solve for r cubed, and we get 4.75 times 10 to the 12 meter cubed, and that gives us a radius of about 16.8 kilometers. Okay. So an entire star explodes. The most dense parts of it remain at the center. That's what's the neutron star, the remnant of that supernova explosion. And you might think, well, if I had that remnant, just the remnant that's left, was the same mass of the Sun, it would only be about 17 kilometers across, or 17 kilometers in radius, so 32? No, 34 kilometers across. So, you could fit it in the city of Dayton, for example. Okay, that's how dense it is. I feel like it's dark in here, so I'm going to open up my blinds. I might as well pause. Okay, hopefully that's a little better. I realize there's this additional complication from teaching from home, is that I'm kind of restricted by the times I have good light. Obviously I have lamps in here, but I doubt they would be bright enough to make this video legible at night. Okay. So the next question, after we know the size of these nuclei. Now that we know the size of these nuclei, the next thing we want to know is the shape. So nearly all elements have spherical nuclei. The transition section of the periodic table is the exception. So these are Z values between 57 and 71 transitions. Okay. They can have an ellipsoidal or oblate spheroidal shape. So ellipsoidal looks like that, a bit like sort of a cigar, and oblate spheroid is sort of like this. Okay, so they can have a cigar shape, or they can have a squashed sphere shape, this oblate spheroidal shape. Okay. But most of the time, we can assume that a nucleus is spherical. Okay. So the next question we might ask is, which nuclear arrangements, or nucleids, I guess that's the name, are stable? So let's draw a little diagram. This is drawn much better in the book, but I will try and draw it also. So if we're going to draw neutron number n on that axis and proton number z on this axis, I'm going to get a line for n equals z, and going down there, so this is n equals z. And it turns out, I'll do this in a different color. It turns out that the line of stability doesn't follow this n equals z like you might expect. It kind of hugs it for a little bit, but then deviates up like so. So this is the line of stability. And just to use as many colors as possible, got a little kind of area around here, irregularly shaped. It's called the area of stability. Okay. So things that are in this region, what do we mean by stability? Things that are in this region are stable for less than a millisecond. Okay, so stability means, well, not like stable like you could just, make yourself a big pile of it. Well, maybe you could, it would just, we'll talk about nuclear decay and how that works in a bit. But so stable means still less than a millisecond. Right? And that's stuff that's inside this area of stability. Things that are on the line of stability are more or less stable. So this is based on experiments, but what's the explanation? By the way, this is actual elements or points on this graph. Right? So they deviate, the line of stability deviates from the n equals z line at about 15. Right, at about 15 proton number. Okay. So I'll write a bit more before I erase. So there are about 3,000 known nucleides, right, different species of atomic nuclei, and 257 have stable ground states. So only a